Greetings. Professor Clare, Chua and I are delighted to present this short video on multiple linear regression. This is following up on the earlier video you might have seen on simple linear regression. We would like to begin with an actual question to illustrate the concepts of multiple linear regression. And the question we would like to address is what determines the price of a house? What attributes of a particular house would determine its price or its value? So with this question in mind, we would like to focus on the use of multiple linear regression. And just for comparison, we would like to point out that there's one basic difference between the two, that is the ordinary and the multiple linear regression. In the ordinary regression model, you have one dependent variable. So is the case with multiple regression. And we assume a linear relationship under ordinary and under multiple linear regression. So these two things are the same. However, under the ordinary linear regression model, we usually have just one explanatory variable, for example, the number of bedrooms. And here, we could have as many variables we would like to have to explain the dependent variable or the variance in dependent variable. So with this said, we would look at the data set. We have this data set from the US, which is Nassau County, which is about 25 miles of east of New York City. The data has the appraised value of the unit, the land area, that is the lot size, and the house size, the square footage of the living space, the age of the house, the number of rooms, the number of bathrooms, and whether there's a garage or not. And we have it's a small illustrative data set of just 30 single-family homes, not a large data set, so just for illustrative purposes only. The first thing to do is to run the descriptives, and you find the mean and the mode and the standard deviation. So the average price is $389 or almost $390,000. The average acreage is 0.24. The average square footage is just shy of 2,000 square feet. The average age of house is 50 years. Number of rooms is about 7, and number of baths is around 2. So these are the mean values, the standard deviations are there. Obviously, the number of observations remains 30. And if you would like to have a look at how the data looks like or appears in SPSS, this is the same data set in SPSS. So the next step is to run the multiple regression. What you have to do is click on Analyze, and then here as this options appear, click on Regression and then click on Linear. And as you click on Linear Regression, it will open up the regression dialog box that you need to populate. The dependent variable is the appraised value that goes under dependent, and then from here you keep selecting the explanatory variables and then adding them to the data set. So age, rooms, and baths. I wouldn't change anything else except I will click on OK, and once I click on OK, the output from regression models appear. Now there is 3 models that I'm going to discuss, and you would see there. It doesn't necessarily have to be like this, but then I would like to present this conversation about how to judge which model to use, what not to use. Let's start with the first model. You have an R square, or let's look at the adjusted R square. I explained these R squares or adjusted R squares in the video about simple linear regression, and you could see that we can explain about 67.5% variance in housing values. And if you look at footnote here, it says that the only explanatory variable we have used is the size of the house, the square footage of the house, and that explains 67.5% of the variance. And if we add to that square footage the size of the lot, that's the acreage, then this explanatory performance or capability increases from 0.67 to 0.75 or 75%. And then in model C, if we were to add to it age of the house, then explanatory variable power of the model improves to 81%. So if you were to answer which model to use, I would pick the third one, because we have 3 relevant pieces of information about our model, and they're explaining 81% of the variance. Then the real thing that we need to focus on is the coefficient. So if you look at the third model, which has the housing size, the land area, so we are ignoring what's on top here. So third model, look at the number 3 explanatory variables: housing size in square feet, the land area in acreage, and then the age of the house. You could see that as the size of the house improves or becomes larger, you see a positive coefficient, and it shows that for every 1 square feet increase, the price goes up by 0.129 or $129. Remember, the price is in thousands of dollars. If the land increases by 1 acre, the price goes up by $276,000. And the age of the house, the older the house, the less expensive it is, and that is known from this negative coefficient here. If we were to look at the t-stats, and they are all greater than 1.96, which means that these variables are statistically relevant, and they are a statistically significant predictor of changes in housing values. The last thing is the conversation about the residuals or the errors, and we make some assumptions in our model, in our regression model, that the model is linear in parameter, and that the model error terms are independent, they are not correlated, and that the residuals or errors are normally distributed, and that there is no and the variance is constant. The predicted value, you can see the mean value is 389. The average residual value is 0, which by default is the case, and that's pretty much it. So I'm going to just skip back for a second to the last slide. If I were to conclude what determine housing values, I would say housing values are determined by the size of the house, the square footage, the land area, and the age. The bigger the land, the bigger the house, the more expensive the house. The older the house, the less expensive it is. And we are explaining with these three variables about 81% variance in housing values.